Yeah, thank you so much for inviting me to speak here. Okay, so today I'm going to talk about elliptic cohomology. So let me start by briefly recapping what happened last time, since it was a long time ago in the previous year. So let me briefly recap what happened with formal group laws and formal groups. So it was established that if you have a complex-oriented cohomology theory, you can produce a formal group law from it. So given a complex-oriented cohomology theory, you produce a formal group law, which is basically like a formal group, but with the choice of a coordinate. So then it was stated that there exists a universal ring with a universal formal group law, the Lazar ring. And in particular, it means that if you consider the classifying step of formal group laws over a given ring, so the R points for given commutative ring are formal group laws with coefficients in R, then this is in fact just an affine scheme. So this is just the spectrum of this Lazar ring MP of a point. This is also the complex cobordism ring. Okay, so that was discussed last time, and also it was mentioned that in fact you can consider the action of a group of automorphisms of formal group laws. So you have the action of this group G on FGL, and in fact the action is free, so to speak. So you have a torsor like this. And this thing classifies, so this is the classifying step of formal groups. So let me maybe discuss now for a bit what it means to be a formal group and, well, just some basic stuff from algebraic geometry. So the most interesting construction for us will be that of a by the way, are there any questions so far? I know that this is probably already well known, and I just wanted to fix the notation. But if there are any questions, please don't hesitate to ask. So now let's do a small discussion of formal geometry. So the most important construction for us will be the construction of a formal spectrum. So we start by assuming that we have a filtered ring, filtered commutative ring. Then we can construct the formal spectrum for this by doing the following. So the formal spectrum of this pair will be just the colimit in the category of free sheaves on schemes, if you want, of usual spectra of quotients with respect to this filtration. So a prototypical example of this is when you take a ring of power series in one variable or many variables, and then you have the filtration by the unique maximal ideal, by the powers of the unique maximal ideal, and then you get the formal spectrum of this pair, which is just the co-limit in this case of dual numbers or rather truncated polynomials over this ring. So how this relates to this whole thing about formal group laws and formal groups. So as expected, you can define the category of formal schemes. So this was the formal spectrum. This gives you formal affine schemes, but in general, you can say that a formal scheme is a directed co-limit of finite dimensional schemes. And this is done in the category of, for example, just 3 sheaves of sets on the category of schemes. So now, if we know what a formal scheme is, we can, of course, define a formal group is a group object in formal schemes. And furthermore, if we want to get some very basic examples of formal groups, the most natural thing you can do is to start from an algebraic group G and consider its formal completion and the identity. So in particular, the relevant formal groups that encode cohomology theories like K-theory and singular cohomology arise in this way. So I don't know if this is a meta example, and then an actual example is that you can do this to, say, GA, and this will produce for you the formal group GA hat with the formal group law that corresponds to just taking a sum. And this is, of course, just singular cohomology, or HZ if you want. And another example is that you can take the multiplicative group scheme and you get, by taking its formal completion and the identity, you get the formal group law that controls K here. And then over the rationals, the Chern character can be interpreted as this exponential isomorphism between formal groups that correspond to the additive group and the multiplicative. Okay, any questions so far? All right. So now let's move on to just discussing this thing in general. So assume that you have some sort of cohomology theory A. assume that you have cohomology theory. Then, of course, you can take A of CP infinity, and this will be some sort of ring with filtration, just as you have for example, singular cohomology. And then from this, you can construct a formal group just by taking the formal spectrum of this cohomology ring. And then you have a morphism like this, which corresponds to the multiplication on your formal group, which arises from the following map on projective spaces. So you can view the projective space as a space of lines in the field of rational functions on the affine line. And then here you have a multiplication map like this. And this induces for you the map from CP infinity squared to CP infinity. So then applying A and then applying formal spectrum, you get the multiplication on your formal group. Okay. Yeah, so we have that. And then another observation that we have to make is that in general, not every formal group comes from a formal group law. So the idea is that basically, well, the formal group law is like a multiplication in your formal group in some specific coordinates. Of course, you can guarantee that you have this sort of formula on the locally. So to assure that in this case, this multiplication is given by a formal group law, you have to require that you require what Lurie calls weak periodicity of A. Namely that you have an isomorphism like this. And then, of course, strong periodicity is the statement that you have that A2 of the point should be a free module. But this is not necessary to, well, get this thing in general. Okay, so now with that thing in mind, we can also say that given a formal group G, one can associate to it a thing which sometimes is a cohomology theory. And this is done as follows. So on a space X, the cohomology theory, or the thing that is supposed to be cohomology theory, is calculated using the following tensor product. So R is the ring of definition. For G, and well, MP is the complex covariance. And why do we have such a tensor product? Well, because as I mentioned before, it was explained that we have this universality theorem for the Lazar ring, which says that basically if you have like any formal group, then you have a homomorphism from the Lazar ring into R, which induces this formal group from the universal one. So you have this homomorphism, you tensor, you get something. And of course, the question now is it true that this is cohomology theory and this is this whole business about Landweber exact functor theory? Okay. And in terms of what we just saw with this picture of having a torsor of this type of formal group laws over formal groups, you can formulate this even more invariantly as follows. So the cohomology theory will be the following thing. So if you have spec R, having a formal group over spec R is the same as having a classifying map into the classifying step, and denote this map by phi. And then the cohomology theory associated to G is just the same as taking the pullback of the quasi-coherent sheaf on M of G corresponding to the complex cobordism cohomology theory along this classifying map. And then the fact is that this exactness condition on my upper star translates into the map phi being a tau. Okay. So that was sort of the recap of what happened last time, and maybe of some slightly new notions from algebraic geometry that are involved in setting up this elliptic cohomology theory, or rather elliptic cohomology theories. Okay. Are there any questions? All right. So let's get into elliptic cohomology. So we saw that in case when the formal group that we considered above is either the formal completion of GA or GM, we get these well-known cohomology theories, singular cohomology and K theory. And now, basically, we can look at this construction for a moment and just say, well, both examples are sort of similar. You just took some one-dimensional algebraic group, and then you produced the formal completion of the identity. Well, can you do more examples exactly like this? And the answer is sort of, well, there's only one other class of examples you can consider. So over an algebraically closed field, we have one other class of examples. Elliptic curves. So these are, of course, non-linear algebraic groups because they're not affine. But you have them, and you can do exactly the same thing. So in principle, you can take an elliptic curve E, take the completion of this elliptic curve at the identity section, and you get some sort of formal group, and you can get a cohomology theory that way. So definition, an elliptic cohomology theory consists of the following data. So you have a conjugative ring, or you have some elliptic curve over R, and you have some weakly periodic cohomology theory in the sense of the above definition. And finally, you have an isomorphism like this, and the formal completion of this elliptic curve at the identity section is isomorphic to the formal spectrum of this cohomology theory evaluated on CP input. And this is an isomorphism of formal groups. So as you can see, saying that an elliptic cohomology theory is slightly more than saying that you have a cohomology theory that happens to be elliptic. You also keep track of this data of some like actual elliptic curve over a ring, such that its formal completion of the identity is the same as the formal spectrum of this cohomology theory evaluated on CP infinity. Okay. So now we can sort of try to do the same approach as before. We can try to look at, well, the classifying stack of like all possible elliptic cohomology theories. But first, of course, we start from just like the regular old classifying stack of elliptic curves. So definition, M11 is the classifying stack of elliptic curves. So maybe that's a good place to say a few words about, well, the things that we're going to do from now on. So in principle, the stock is supposed to incorporate some elements of derived geometry, and in particular, we'll use the language of stacks. So I think in this case, this is a very classical stack. So this is a stack in groupoids. But in principle, we will consider just sheaves of spectra, and we'll call these stacks. So you have some sort of, so given a site with authentic topology, for us, this will be just like the regular site of regular in an imprecise sense. It's not a mathematical term, just regular set of affine schemes with Zariski topology. You can get the category of stacks or homotopy sheaves or infinity sheaves, whatever you call them, as just the category of all the full subcategory of all pre-sheaves that satisfy the appropriate version of the sheaf condition that you build by considering the check nerves on this site. Okay. So with this in mind, in particular, if you consider M11, its value on a ring R, or on, if you want, on the affine scheme spec R, is the groupoid of elliptic curves over spec R. Groupoid of elliptic curves. So in particular, it's one homotopy type, and you can view it as a spectrum. And you get a step in the previous sense. Okay, so now from this we can construct the following functor. So if you have M11, you can consider its étale site. So this is the category of all maps like this, spec R into M11, which are étale, and then obviously like the morphism circulative triangles. And you can consider a functor from this category into the category of cohomology theories, which sends, well, a morphism like this into a cohomology theory constructed as before. So you have this map phi, and then from this you can construct, well, so if you have a morphism like this, you can construct a formal group scheme just like by pulling back the universal elliptic curve to spec R and then doing that thing that we discussed. So you get a formal group, and then because this map is étale, the functor will be exact. So in particular, you get like an actual cohomology theory and not just some sort of functor from the category of topological spaces. Okay. So maybe another thing that I should mention here, so you might ask, why do we even expect existence of like many étale maps from affine schemes into our step? And the reason why this works M11 is a Delaunay-Mumford stack. What that means, I'm not going to give a technical definition. I will just say that it's a non-algebraic or default, which means that basically you can glue your stack from affine pieces with maybe only a finite stabilizers of points. So in particular, it means that, well, you have the aforementioned affine pieces, they map into your stack, and they give you a tau maps into your stack because, well, the stabilizers are finite. Okay. So now, after we constructed this functor into cohomology theories, of course, it's natural to ask, can we get something better? Because this whole notion of a cohomology theory is somewhat strange and artificial. So the question now is, can we, instead of considering a functor into cohomology theories, consider a functor into spectrum? So obviously, if you have a spectrum, you can construct a cohomology theory. And then the question is, can you find a lift like this? And the answer is, well, it's unclear, because viewing cohomology theories just as is, as additive cohomology theories, is not giving you enough structure to answer this question. However, you can instead consider another version of this question. So actually, every cohomology theory we constructed was multiplicative. So it's natural to think that they come from, not just from spectra, but from commutative algebras and spectra in appropriate infinity categorical sense. So these are infinity algebras. And then, of course, you have the same functor into cohomology theories with multiplication. And now the question becomes, do we have a lift like this? And the answer is yes. So we have the following theorem. And due to Gauss Miller, which says that in the previous setup, so if you have the tau side of your classifying stack, there exists a unique up to homotopy lift to commutative algebras in spectrum, which is denoted by this OM derived. So notice that before that, well, for say GM and GA, you had a certain uniqueness. So like in some sense, the classifying stack of all GMs over a given ring is trivial. You have just like one GM. But for elliptic curves, you have many different elliptic curves over the same ring. And so the construction of this lift sort of gives you the universal elliptic cohomology theory. So it doesn't itself correspond to any one elliptic curve, but rather to all of them at once. So OM derived gives you the universal elliptic cohomology theory. or even more concretely, to get an actual cohomology theory, because this is not a cohomology theory, this is merely just a functor from one category to another, you take the colimit, or, well, the homotopic colimit, but every colimit is a homotopic colimit. So, yeah, so you take the colimit of this functor and you get the following cohomology theory. So this is the theory of topological modular forms, where you invert primes 2 and 3. So topological modular forms with 2 and 3 inverted. And then the reason, well, this is called topological modular forms is because you have a homomorphism into integral modular forms. Sorry, saying something wrong here. So this is sorry. So this is the cohomology theory of topological modular forms where you inverted something, and then you have the theory of just like actual topological modular forms where you don't invert anything, and you have a homomorphism into integral modular forms that becomes an isomorphism after you invert 2 and 3. Okay, so let me summarize what just happened. So the idea was that we wanted to consider one-dimensional formal groups. In the previous talk, we considered GM and GA, and we've got K-theory and senior cohomology that way. And the only remaining case that we had to consider was the case of elliptic curves. And it turns out that in some sense you can consider the universal cohomology theory corresponding to elliptic curves, and this will give you this TMF with delta inverted. So maybe let me write this down. So all one-dimensional algebraic groups over an algebraically closed field are GA, GM, and elliptic curves. This gives you singular cohomology, this gives you K-theory, and this gives you this, well, elliptic cohomology. And by taking the universal one, you get this TMF with delta invert. And to just get TMF, you have to further, instead of the moduli step of elliptic curves, you have to consider its Deligne-Mumford compactification, which arises when you allow your elliptic curves to have nodal singularities. Okay, so now let me maybe sort of give you a glimpse of what's to come, and also to discuss the right geometry for it. Okay, so now, since this is a seminar on equivariant elliptic cohomology, the question that we want to consider is how do we build an equivariant version of everything? And, well, you can have multiple answers to this one. So one answer, which stands for Borel or boring, is the following. Well, just consider your cohomology theory, you want to evaluate it on a space with a G action. Well, you can build like a free action out of this one. So you can take X, multiply it by the universal bundle of G, and then mod out by the diagonal action. You get something with a free action. So, sorry, you get the, so if you just multiply it by the universal bundle of G, you get something which is homotopy equivalent to X. And then when you mod out by the diagonal action, the action is free, so you get a free quotient. And since you expect that if you take an equivariant cohomology of something which is which has a free quotient, the result should be just the usual cohomology theory on the quotient. So by this logic, after you do this, to get the Borel or Boring equivariant cohomology with respect to the G action on X, you just need to apply the usual cohomology to the Borel construction, i.e. to this quotient. And why this is not so great? Well, why this is boring? The answer is that actually maybe you want your equivariant cohomology theory to correspond to some actual equivariant data, like equivariant K theory supposedly should correspond to equivariant bundles. And this is not what you get with Borel cohomology. So let's consider an example. So here you have just like genuine equivariant K theory where you have bundles which are equivariant, you do K theory with them. And then you have the following thing. So you get a map into this X times EG, which comes from the projection to the first coordinate. And then this thing, of course, will be equivalent to just the regular K theory on EG, on the quotient of X times EG by G. And then this, of course, is just the same as the Borel construction. So this is K Borel of X. And let's see what this actually does. Let's assume that X is a point. Then on one side, you have the representation ring. And on the other side, you have the K theory of G. Of course, if your group G is non-trivial, these are not the same things. So in some sense, the question becomes, how do we find this site here in general? So let's look at this a bit closer. So consider G equal to S1. Then, of course, we know that BG is CP infinity. And, of course, we know what K of CP infinity is supposed to be. So K of CP infinity will be the ring of formal power series with integer coefficients. And on the other hand, the representation ring of S1 will be just the ring of Laurent polynomials, where chi is the inclusion of S1 into Z star. The reason being, of course, that S1 is an abelian group, so every irreducible representation is one-dimensional, and then any one-dimensional representation is a power of this one. Okay. So now we have a homomorphism like this. And what it does, well, this is incidentally also the ring of functions on GM. And, well, this is the ring of functions on the formal completion of GM and the identity. So this thing is just the same as taking the formal germ. So now, inspired by this, we can rephrase the previous question as follows. So, question, how do we build an equivariant cohomology theory becomes how do we integrate a formal group? Because truly what happened here was that we had a formal group. That's just the regular K theory. And then what we want is a non-formal group, like an actual algebraic group. And so to find, for example, an S1 equivariant version of a cohomology theory amounts to finding an actual algebraic group that corresponds to your formal. Okay. So now I believe that before the next talk, I should. I guess I can say now that this was sort of the conceptual punchline of my talk. So if there are any questions, please feel free to ask. Other than that, I can just now spend the last 10 minutes by giving some sort of like general background on derived algebraic geometry. There are no questions. Okay. So the final part of the talk, derived algebraic geometry. So in very basic terms, you can summarize everything that is happening in derived algebraic geometry by saying the following. So in algebraic geometry, you have commutative rings. In derived algebraic geometry, you have infinity rings or commutative algebras and spectra. And then in some sense, you can say, well, let's just like consider affine schemes to be the formal duals of commutative rings in whatever sense we consider them. And then, well, if you want to build some sort of Grothendieck topology, you know how to do it on commutative rings. So let's just take phi naught of the infinity rings, you get the commutative ring, and then you can define the Grothendieck topology from a Grothendieck topology on the usual commutative rings. And that gives you a set of derived affine schemes, and from that you can build derived algebraic stacks. And that's basically it. But to be slightly more, I guess, rigorous and slow, let's consider how it's actually done. So on this side, if you have a ring A, you can build spec A, which will be some sort of locally arranged space where this is a topological space of prime ideals in A with the sheaf of rings induced by A. And then here, well, if you have an infinity ring A, you can also build spec A, which will be an infinity coherent space. So, as I said before, basically the procedure is the same. So as a topological space, this will be just prime ideals in the zeroth homotopy group of this infinity or infinity spectrum. Prime ideals with zeristic topology. And then the sheaf of infinity rings just once again comes from A, because, well, if you have an element in pi naught of A, you can localize the whole ring with respect to that element. And that means that this whole ring localizes over the spectrum of that ring. So now we build, in the classical and in this derived sense, we build some locally arranged spaces, and then one defines the heuristic topology by saying that a family of morphisms between affine schemes is a covering if size are localizations or open embeddings of Y or in Y. And they're jointly surjective. And so for E infinity, you just do the same thing, just say everything with respect to taking pi naught. So basically the idea is that whenever it comes to defining some sort of covering families in derived geometry, you just go back to the classical setting by taking pi naught, and then in classical setting you have all these notions like Zariski et al., etc. Okay, so now definition, the category of derived steps on affine schemes. Is, well, as I mentioned before, three sheaves of well, that's actually a good question. So I guess you can do pre-sheaves of spectra on affine schemes satisfying the sheaf condition, or you can do, I guess, maybe more classically, you just do pre-sheaves of connective spectra or anima that satisfy the sheaf condition. In any case, the idea is that we take some sort of sheaf category of homotopical nature on your side of affine schemes. So in particular, for example, as we've seen before, with all these moduli steps, you just need sheaves of groupoids, so it's sufficient to consider sheaves of anima, for example. Okay. So we have that, and I don't know if I want to say anything more about this. So I think yeah. Yeah, I think that that's pretty much it. Okay, all right. Thank you so much. Are there any questions?
All right, so let's thank the speaker again. Are there any questions? All right. Then if there are no questions, we'll meet again next week.